So here we go. That's me, Yuan-Pei. Here's our textbook. This is very, very widely used textbook, Discrete-Time Signal Processing by Oppenheim, Schaff, and Schaeffer. Okay, and then I would like to cover some details about the things in the class. First of all, like I told you, we have some videos that you can watch. And I think the length of the video is the total length is about, I would think about 1 hour plus minus. Sometimes it will go to 1 hour and a half, okay? But sometimes just about an hour. But do keep in mind when you watch the video that it's actually the material of a whole week. So it's like a 3-hour lecture, and that's condensed into 1 hour. And the reason that it can be condensed into 1 hour is because during class there will be questions and there will be discussions, but when I was doing the videotaping, there's nobody to ask me questions, so all the time is condensed. So when you watch the video, do keep in mind that although the video may last only an hour, it's really a 3-hour lecture, and to try to treat it as a 3-hour lecture. So when you watch the video, sometimes I ask some questions during the video. You try to pause the video and think about the question that's raised in the video, because that's how we would normally do in lectures. We will keep some time. We'll leave some time for students to think about the question that we asked during class, and then you can think about and reorganize everything and then maybe come up with your own answer. So do pause very often when you watch the video, okay? And I would strongly encourage that you take your own notes. Take your notes just like you would in a regular lecture when you are watching the video. The lecture notes will be very helpful when you try to get organized, and we will also, during class, when you're doing homeworks, it's actually, we will talk about that later, but sometimes we will have a lot of discussion. And when we have a discussion, it would be the best if you have your lecture notes, and we will use the lecture notes as a reference to start our discussion, to base our discussion on. Okay. So please do take your own lecture notes when you watch the video. Have you ever done some experiment, and when you look at the result, you have no idea whether it's correct or not? Could it be possible that you have no idea? Oh, I generate a plot, but whatever it is, I don't know. Does it ever happen? Oh, well, that's going to change, because when you don't have any idea about what you have plotted, what does that mean? That means that you are not expecting anything. Okay. When you do the programming, first you have some expectation. You expect a certain output. You expect a certain result. You expect to behave in a certain way. So when you don't have expectation, then you don't have a feeling for whatever that you have generated. So first, you have feelings. You have feelings. You have intuition about what you're going to generate. And then when you look at the plot, you would have some reference because you have expectation. Your expectation is your reference. You compare that with your expectation, and then you say, oh, this makes sense, or this doesn't make sense. But if you don't expect anything, if you are blank in your heart, if you don't have feeling, well, this seems to be a strange word to talk about in an engineering class, but somehow this is the best that I can put forward. Feeling. You need to have feeling, and you need to have intuition, what is going to come about, and then you can have some judgment whether this is natural expectation or not. Discrete-time signal processing. That's our class. Okay? So, judging by the name, we are processing some signals. Processing of signals. Processing of signal. Okay. Well, that doesn't sound like much, right? What do you expect that we are going to be processing? What kind of thing are you expecting that we will be processing? You think we might be processing. That's worthwhile processing. So first of all, signal. What kind of signal do you think might be relevant in our discussion? So give me some examples of signals. Yes, thank you very much. Force. Yes, you may have some measurement of force, right? So signal, that's very good example, and I think that's some signal that may be very useful in control engineering, right? Okay. Any other example of signals? Voltage, yes, voltage, very, very important. Voltage signal. Voltage is a signal, that's very good. All right, discrete-time signal processing, and the second line doesn't convey the whole thing, right? What is the key word that's missing? Discrete-time. Discrete-time. Can I have some example of discrete-time signals? Yes? Video. Thank you very, very much. Yes, video is an example of discrete-time signal. Video is an example. Any other example? Analog to digital converter. Okay, analog to digital converter. At the output of analog to digital converter, we would have a discrete-time signal, that's for sure. So if we have an analog to digital converter, and the output, we would have a discrete-time signal. Okay. Well, that's a big category. So what can be the output of an analog to digital converter? What could be the output? That's a really, really big category. So what is it? What kind of signal would you put it through an analog to digital converter and then you get a discrete-time signal? Any such example? Yes, thank you very much, because you just mentioned force, you mentioned voltage, and those signals are in general continuous time signal, and we can put it through an analog to digital converter, and then we will have discrete time signals of voltage, of force, of whatever. Okay. And video, and in video usually it's not just the image, right? You would also have sound to go with the image, right? You don't watch a silent video, right? You would have sound to go with the image, and that sound, that could be music, will be the output of an analog to digital converter nowadays. Okay, nowadays that's what we have. All right, so what do you expect that we will be processing the signal with? What do you think is used to process the signal? DSP. Yes, that's a very good answer, DSP. Anything else? Sampling, okay. Sampling, so by sampling you mean the first we sample and then we convert it to A to D to D. I would say that's part of the processing part, right? That's part of the processing, yes. So we are using what we will be are we going to process the signals by hand? I mean, you compute the signal by hand, right? So do we do that? No, we don't. So what do? We use well, he says something. He says DSP, right? That's a possible device. We can use computer. Okay, and that computer can take many forms. It can take the form of a DSP, it can take the form of something more primitive. Okay. Alrighty. So when we are processing signal using computer, then we bear in mind that we are using a computer. And so what can be the main components of a computer? Main components of a computer. I think you have taken computer in the first year, right? Freshman year. So what are the main components of a computer? CPU. You have CPU. And then what do you have? What else? Memory. You have memory. You would have memory, right? Memory. Okay. So, in memory you would have a shift register, right? Have shift register. So in this class, when we are doing all sorts of things, bear in mind that's the thing. That's the thing that we are playing with. We're going to have memory, and we are going to put the signal in the memory, shift register, and then we're going to do some processing. Okay, so that's the thing that we do here. All right, well, that brings me to another topic. What do you expect to learn in this class? What sort of thing do you expect in this class? Do you think it's going to be a math class? Or what do you expect? Well, actually, it has a lot of math. It has a lot and a lot of math. Okay, so this class can be taught with math from day 1 to the last day. Okay, so it's going to be a class with a lot of math. But the thing is, this is not a math department. This class is not offered in math department. It's offered in an engineering department, right? So when we are learning this math, those are tools that we communicate. The tools that we communicate to our classmates, our fellow classmates, the tools that we use to communicate to me, mathematics is the tool here, is the language here. It's not something that we don't want to learn math for the math's sake here. We learn the math because we have a mission, we have a purpose. So whatever math that you learn in this class, it has a purpose. If for any reason during the course of this semester that you feel like you are learning math, not engineering problem, then stop. We need to get a check here because you are not really learning the class, because math is not the objective here. Math is something we use to communicate. Math is something that the language that we use, but it's not the end of it. This class is not about math. Okay. All right. So we are learning processing of signals using computers. That's the thing in this class. But what do you think we are going to process the signal with in this class when we are doing homeworks? What do you think that we're going to be using when we are doing homeworks? Remember, there's no electronics in this class. Well, except me. I can bring electronics. I will need to bring computers from time to time, but nobody else. So what do you think you can use to process signals in this class, in this classroom? That's right, picture. We were going to have the pictures. And the pictures are really good for illustration, and it's really good for understanding. And when you are doing homework in this class, we don't have computers, right? So we will be using just by hand computation. We don't have computers here, and we are going to do all the processing by hand, by brain. Okay, so that's the thing that we're going to be using in the class, which is good. Why it is good? Because remember that when we said that even if we do MATLAB, even if we do simulations, we still want to have some idea before we do the coding. We still want to have some idea before we generate the plots. Okay? And how do we get those ideas? Because we computed it in our mind, we computed using our brain. So that's how we get the picture, how we can have expectation of our plots, of our results. Okay? So although this class is about computing signal, processing signal by computer, we will do handwriting in this class. We will do just compute by hand. Okay? And just now you mentioned some examples, continuous time signal, and also some example of discrete time signals, and you also mentioned A to D converter. So let's just give you an example of how discrete time signal come about. Okay, for example, we have a signal T, all right, a signal that varies with the time. So for example, this is the street noise level. Street noise level. Street noise level. And we have an XCT. So here we have XCT. Okay, a continuous time signal. Usually for continuous time signal, we put a subscript of C to indicate that it's a continuous time signal. Street noise level. So do you know that the unit that usually goes with the street noise level? The unit that usually goes with the street noise level? It's usually given in decibel, right? It's usually given in decibel. Okay, so what would be 就是我们在那个就是那个街道上面，你可能会去记录它的那个有多吵嘛啊，然后可能说是多少分贝这样子，大概安静的大概是多少分贝？可能也许大概40左右吧啊。Okay, so let's just imagine that we are on Guangfu Road at midnight. At midnight. So at the start of the time. That's the beginning of a day. So at midnight it's supposed to be quiet, right? So it's quiet. Quiet. So let's say this is a 40 here. It's pretty quiet, and then a car is coming, so it gets noisier. And then we have two people racing motorcycle. So ooh, it becomes very loud, like this. And then they left, so it resumed its usual quietness. And then, oh well, maybe we would have car. We would hear tire screeching. Boom. And then we would have, there are two cars bump to each other, but it's not too serious. So we hear car door boom, boom, and two people coming out arguing. Okay, like this. So this will be the street noise level, right? And we can record it in time and say this is only, we recorded only about, this is the first 60 seconds, okay, of the beginning of the day. Alright, so this is 10, 20, 30, 40, 50, and 60. Alrighty. So this is a continuous time signal. And then, can we store such a signal in computer? Entirely. The entire signal in computer. Can we do that? No? No. What's the problem? Another thing is, if we want to store the whole analog signal or continuous time signal, we will have to store the signal at 0 and the signal at very close to 0, very, very, very close. How many value do we need to store in a computer to store the whole thing? How many value? Infinite many, right? There will be infinitely many, even in 1 second. Okay, there will be infinitely many values we need to store if we want to store this analog signal. Okay, so usually we take samples. Like just now somebody mentioned that we take samples. So let's do that. So one way to do it is we take samples. For example, we can take samples every 10 seconds. 10 seconds, the unit here is second. Okay. And 10 seconds we take another sample. 20, another one. And then 30, another one. 40, another one. 50 another one, and then 60 another one like this. So we can take samples. So in this case, T is equal to 10n. And then we would have a discrete time signal. A discrete time signal. And when we take samples, this is called sampling. When we take samples. And let's first draw this figure for xn. Okay, guess I don't need this. This is n, and this will be xn. When n is equal to 0, this is 0, this is 0, so t is equal to 0, right? So that would be the first sample that we have right here. So this first sample here is 40. So that's 40 right here. This is 40. Okay? And now when n is equal to 1, that will correspond to this value here. This value here. Okay? So slightly larger than 40. Okay. And in discrete time, when we draw discrete time signal, usually we draw it like this, because it's a samples by samples, not like this one. Okay, this is a discrete time, we draw it samples by sample, and this one is continuous, so it's all connected together. And at n equal to 2, that would be this one here, and that's a little bit higher. This is 2, that's right here, 2. And then 3, 4, 5, around the same value, that's 6. Okay, so that's xn. All right, and now can we store such a signal on computer? Can we store such a signal on computer? No. Somebody shook his head. Why not? You already said that, right? Because this is a 40, and this could be, let's say, this is a 40 1/3. Right? 40 and 1/3. And can we store an arbitrary real number on computer? Can we do that? We cannot, right? That would take infinitely many bits. So maybe we will round it up. Maybe we will round it up. This is x prime of n, okay? And say after rounding, this x prime of n is round, xn with a rounding. Xn with a rounding, okay? We just round it to the nearest integer. So we may still have 40, and this one is a 40 and a third, so this is again 40, and then after rounding, all these are integer value. 0, 1, 2, 3, 4, 5, 6. If this is 40, this is still 40. 40 and a third, it will be rounded to 40 as well. Okay. And with this rounding, then this sample value, would it still be the same as the values here? The values will be different. And that's what we say quantization error. Quantization error. This is what we say quantization. When you heard about signal processing, you usually heard about digital signal processing or discrete time signal processing. Which one did you hear more often? Digital signal processing or discrete time signal processing? Digital signal processing, right? Okay. So this is what we call a digital signal. A digital signal. This is what we call digital signal. Sometimes I use abbreviation. SIG stands for signal. These is A, discrete-time signal with quantization. Now we talked about signal part, right? We get example of the signals, and that's one way to obtain discrete-time signal by sampling. And actually, a lot of signal that we may be processing are obtained this way. We sample a continuous time signal, and then we get discrete time signal. Okay, so we talked about signal, now comes the processing part. What kind of processing do we do? What kind of processing do we do? We have the signal on the memory, right? And then we do what? What kind of operation we may do to a signal? Just a very simple one. For example, you have your CPU, right? And you have some process, you just want to, you have your data on the shift register, then what do you do? What do you do? What kind of thing do you do? Basic things. Scale, okay, you may multiply, right? Multiply it with a number. Okay, very good, we multiply. And something simpler than multiplication is addition. So we do addition and multiplication. So processing, now for the processing part. We may have addition in here. We have multiplication here. And then we also need memory. Okay, first we have to have the data on the memory, right? So, and also memory. And that's all there is to it. Just addition and multiplication and some memory. That's all the thing that we have in the system. Okay. And if this is xn, like for example, the xn that we have here, and the output is yn, this is a discrete time. Discrete time input, discrete time output. Then we say this is a discrete time signal processing. This is a discrete time signal processing. This is a discrete time signal processing, okay? And if instead this is x prime n, digital signal. This is a digital signal. We already do the quantization. This is already a signal that can be stored in a computer. Then this is x prime n. We apply to the system, and the output is also a digital signal, y prime n. These are all digital signals. These are all digital signals. Then this is digital signal processing. Digital signal processing, okay? Then we would have digital signal processing. So what kind of signal processing are we going to be discussing in this class? Discrete time signal processing or digital signal processing? Well, it says discrete time signal processing, right? It says discrete time signal processing, and our textbook is also discrete time signal processing, okay? So, but how about digital signal processing? Okay, digital, then we will have to talk about how are numbers stored in computer. We know in computer we would have those, we have a different representation of numbers, right? In computer, and we have different number of bits to represent a number. Okay, so for example, if we have, usually the number are stored like this, right? We would have sign, and then we would have significant, And then we also have exponent, significant and exponent, and also a sign. And then we would have, so for example, we have a 30 bits representation, then it's probably sign bit. We would have a 1 for sign bit, and then 23 for significant, and then 8 bit for exponent, and then 8 bit for exponent. If it's 64 bits, then we have 1 plus 52 is significant, and then 11 bits for exponent. Okay, so if it's a high resolution representation like this, what do you expect the quantization error here to be? If we have so many bits to represent a number, then these two should be close, should be very close, right? So usually when we talked about processing, when we discuss the principle of processing, we usually talked in the context of a discrete time signal processing. Okay? And in the case of a high resolution number representation, there's very little difference between the two. But then there are some applications when you are shooting for low resolution representation. Okay? Then you have only a limited number of bits to represent each number. Then in that case, quantization error need to be taken care of carefully. Okay? But in this class, we will talk about discrete time signal processing. We will talk about just a little bit about consideration in digital signal processing during the semester. Okay, I think there will be some part, at least we will see some example and talk a little bit about quantization. All right, so during the course we will have, first of all, we will talk about consider signal processing in time domain. So first we will talk about in time domain. Okay, and that's what we will be talking about in chapter 2. Chapter 2, this is part 1 of chapter 2. Okay, and then usually we need some tool for analysis, right? And I think you must have a lot of experience with the signal processing for continuous time signal. What is the tool that you use when you want to see through the signal? See beyond the signal. Well, the signal is right there like this, right? You look at this. Okay, this is a time domain representation, but sometimes you really want to see right through. Just like a person, you want to see what's on his heart, right? On his mind. So what is the tool that you might be using to see through that? To see through the signal. Any tool? In continuous time, we talked about time domain processing, right? And what else do we talk about? Frequency domain, yes, thank you. And that will be frequency domain. And that's, we're going to introduce a tool, Fourier transform. Fourier transform. And that's chapter 2 also, and that's part 2. Okay. And then, just now you talked about sampling, right? We talked about sampling. That's how we obtain a lot of a discrete time signal. So we're going to talk about sampling, how to sample. Just now, we have this example here, right? This is a street noise level. This is what it looks like in continuous time. And this is what it looks like in discrete time. If we sample every 10 seconds, if you really want to understand what's going on the street, do you think this will be enough as sampling time? It's not enough, right? It completely leaves out the accident part, right? It happens, the accident happened only in a few seconds. If you just leave this out part, then there's no recording at all for the accident part. So obviously, this is not enough sampling. We are not sampling fast enough here. All right, so how to sample? That's what we will be talking about here. All right, sampling, that's chapter 4. And then we also do, and then we will try to see how do computer compute. Here, a Fourier transform is an important analysis tool, right? But like we said, usually when we do the processing, we do the analysis, we do it on computer. So how do computer compute Fourier transform? That's what we are going to talk about in chapter 8. Okay, how do computer compute Fourier transform? And then, well, let me try to refresh your memory for continuous time again. You have Fourier transform for signal analysis, right? And then any other tool that you may use for continuous time signal and systems. Usually for signal analysis, we use Fourier transform, right? And when it comes to system analysis, what's the tool that's usually used? There's a tool. What is that name? Is there a tool? 示波器. Oh, 示波器. Yes, you're talking about a device, right? Okay, that's good. Yes, 示波器 is a good tool for looking at the signal, right? System analysis, something like a Fourier transform. Yes? Z transform, continuous time signal. Laplace transform, yes, Laplace transform. But I'm not writing down Laplace transform here. What I'm writing down is what you said, Z transform. That's the equivalence of Laplace transform for discrete time signal. Tool for system analysis. And that's Z transform. Excuse my handwriting. Z transform. Well, you say Z transform. In the first place, you must be a very digital person. And this is chapter 3. All right, that's the tool. And then we're going to analyze the system. How to analyze system. That's chapter 5. And then we're going to talk about implementation related issues. Implementation. That's chapter 6. And then filter design. That's chapter 7. Okay, so that's what we are going to do in this class. And we will do this in this order. So it's going to be 2, 4, 8, 3, 5, 6, 7. And these chapter numbers refer to the textbook that we are using.